Okay. So we covered a fair amount yesterday. So in comparison, today will be a relatively light lecture. This is the last one that you're responsible for on the exam on Monday. So we've talked about structure and function of fibrous proteins, and then we moved into globular proteins with myoglobin and hemoglobin, where they're simply binding something and releasing something. So we're ultimately going to move towards enzymes and how enzymes bind their substrates and chemically transform them. So before we actually get there, we want to go over and learn something about the basic concepts regarding catalysis and what it is that enzymes actually do. So we'll go over a brief intro to catalysis, looking at the free energy profiles and what enzymes do, and then we'll start talking about reaction orders, which are basically the concentration of reactants that the reactions are dependent upon. We'll go through first order, zero order, and second order kinetics, and then we'll start to get into how it is that we actually measure and analyze the kinetics of an enzymatic reaction. Okay, so let's just start out with a simple proton transfer. All right, so I think in the text I said a base, but remember a base is an acid, and an acid is a base depending upon whether it has the proton on it or not. So in this case, B1 has got a proton, and it's going to transfer it to B2. At some point, okay, in going from here to here, it's going to go through a transition state where the proton has dissociated from B1, but it's not fully bonded with B2 yet. All right. So this is an energy maximum, and what we have to appreciate, okay, is that when we talked about basic thermo in lecture 1, right, we talked that we'll have our reactants going to products, and we have a free energy change associated to that, right? That energy change, what did we say that was related to? Well, there's an entropic component, there's an enthalpy component, right? But the equilibrium constant. So that delta G, and then for the standard state that we talked about, we called it delta G0. So delta G0 is telling us something about the equilibrium constant, if you remember. That is a reflection of the intrinsic reactivity or reactivities of the substrates, right? So when we get to equilibrium, the equilibrium constant tells us what? The relative amount of products over reactants, all right? So in going from this initial state to the products, the equilibrium constant doesn't tell us anything about what? How quickly it gets there, right? It tells us when it gets there, this is going to be the ratio of reactants and products at equilibrium, but it doesn't tell us anything about this process in going from the reactants to the products. So in the last example, where we've got a proton transfer and there's a transition state, this is characteristic, okay, of the energy changes associated with a chemical reaction. So we're going to define a second term, which is the energy of activation. All right, now that energy activation is this term here. All right, that is the height of the hump. All right, so you have to get over the hump, this energy barrier, to ultimately get down to products. All right. When we talk about energetics, if something has a higher energy, is that more stable or less stable? If it has a higher energy, is it more stable or less stable? Less stable, right? You wake up in the morning, you either sit on the couch or you drink a gallon of coffee. You have a lot more energy. You're going to be less stable than if you're just kicking back and doing nothing on the couch. Everything wants to go downhill energetically, ultimately, right? So this transition state is during the process of the reaction, and we'll see especially for enzymes, it has to rearrange. Chemical bonds are being distorted, broken, new ones formed. And so that actually has a higher energy level. So then the question is, if delta G0 is telling us something about the equilibrium constant, which we refer to as a capital K, this delta G double dagger, or this energy of activation, that's related to the rate constant little k. All right? So remember, equilibrium constant, reflective of the delta G, large K. The rate at which the reaction occurs is going to be dependent on how high this bump is. If this has a very high energy of activation at any particular point in time, you have a small number of molecules that have enough energy to get over it, right? So the rate is the rate at which these little ants or whatever are able to finally get up and get over the top, all right? Lastly, the velocity of a reaction. So this one, A going to B. The velocity is going to be equal to the rate of appearance of product, which is the same as the rate as the disappearance of the reactant A, and that is going to be equal to this little k, which is the rate constant, times the concentration of A. So as the reaction is going, this velocity is going to be determined by, and when we say velocity, what are the units for that? The concentration per second, right? You're getting a change in the molarity or the concentration of a product with respect to time. Right? Okay, so what we're talking about here is catalysis. So we have some examples, which we're not going to go over, where you have chemical catalysis, where you can, bless you. You all right? All right. Where you can add a chemical, and the chemical will help catalyze the reaction, right? Enzymes are, in fact, protein catalysts. So this is ultimately where we're going. They increase the velocity, or they accelerate the reaction, but they themselves are not altered. They cannot change that equilibrium constant. Bless you. What they're doing is, as you, well, we'll get to it in a minute. They are changing the rate constant, but the way that they're doing it, they're changing the rate constant for the forward reaction, but for the reverse reaction to the same extent. And so it does not change the equilibrium constant. It doesn't change the reactivity, the intrinsic reactivity of the reactants. It simply says, whatever that equilibrium constant is, in the presence of an enzyme, we're going to get there faster with the enzyme being there. All right, this point here, they themselves are not altered. If you think about a catalyst, you should know a little bit about catalysts. If you have a reaction and you want to catalyze it, how much of the catalyst do you put relative to the amount of substrate that has to be converted? You normally just put a little bit in, right? Because it's catalyzing it, and it goes through multiple rounds of catalysis. So what that tells you is whatever the structure is of the catalyst, and this is going to be especially true for enzymes, when we say they are not themselves altered, that doesn't mean that they don't undergo alterations during the process. What it means is when the process is over, it has to be back in the state it was at the beginning. If it's not going to be chemically or structurally suited to start another round of reaction. So when you think about a catalyst or an enzyme, you say it's not altered, and then invariably someone will say, wait a minute, it's being modified, it's binding the substrate, there's a covalent bond here. It does undergo changes during the reaction, but it has to be regenerated back to its initial starting point so that it can do multiple rounds. So that's what we mean by they're not themselves altered. Okay. So in a non-catalyzed reaction, we have that energy profile. What is it that enzymes are doing? How do the enzymes accelerate a reaction? They do it by decreasing the energy of activation. Jesus, everybody's sneezing. Get the sickness out of your system before the exam on Monday. So this delta G double dagger, right, if this hump is lowered, then at any point in time, you're going to have a greater number of molecules that are going to have enough energy to get over the hump. So that's why you have an increased rate. Now, if you want, this is a hill. If you have a hill and you want to decrease the height of the hill, there are two ways to do it, right? One would be to make this hill not so high. When we talk about delta G double dagger, it is the energy that these molecules have to overcome to get over the hump. Another way, okay, so if we wanted to bring that hump down, and this is the transition state, if we want to lower it in energy, is that going to be a more stable or a less stable structure? More stable. So you can start thinking ahead that what an enzyme can do is normally, let's say you have a substrate or two things coming together, that as they go through that transition state, in the absence of an enzyme, they have a certain energy associated with that instability, but if the enzyme's active site is structured in such a way, side chains complementing things, charge, so forth, if it stabilizes that intermediate, then what's it going to do to the energy? It's going to drop it. And so if it drops the activation energy through a stabilization of the transition state intermediate, then you're going to have an increased rate. You could also do it by raising the energy of the reactants before the transition state. All right? We're not going to talk about examples of that, but you should appreciate that if it binds them in such a way that raises their ground state energy before they go through the transition state, the energy required to get over the hump is still going to be less. Rather than pulling the hill down, you're starting with the reactants and increasing their energy. You're destabilizing them so that it's easier to get over the hump. All right? The important point is the energy needed to go from where the reactants are over that hump, that is what is telling you what the small k rate constant is. Okay? All right, so let's look at some terms. So here we're not talking about enzymes yet. We're simply talking about chemical catalysis or chemical reaction. There's no enzyme here mediating this. So the velocity, we already said, okay, is the rate of change or the rate of loss of reactant, which is equal to the rate of appearance of the product. You accurately pointed out that the units for that is molarity over time. So we said that this first order reaction is equal to, the velocity of that is equal to some rate constant times A. The reaction order, the reason that this is first order is because to get the velocity, you're taking a rate constant, but then you're multiplying it by the concentration of reactant or reactants. In this reaction, if you have a rate constant that's telling you something about the energetics of going from A to B, that rate constant, you're going to have to multiply it times the concentration of the reactant. And in this case, you only have one. So if it's small k times the concentration of A, this reaction is what order? It's first order. So if it's first order, then you could say, well, I know that my velocity has to have those units. If the rate constant is being multiplied times the concentration of A, the units for A is what? Molarity. So then the first order rate constant has to have the units of per time, per second, right? So a rate constant for a first order reaction would be some number per second. We can look at this and we could say, what is the order with respect to the reaction, i.e. the overall order, and that's a first order reaction. We could also ask the question, what order is it with respect to A? And in this case, it's the same, right? First order with respect to A, first order overall. It's dependent upon the concentration of A, first order with regards to A, but it's not dependent on the concentration of anybody else. So the reaction overall is first order. Okay. So what are the manifestations? Let's say you have some reaction that's going on and you're not really sure if it's first order or not. You can basically do an experiment and look at the rate of appearance of product or the rate of loss of reactants and plot it out to see what the order is. All right. So we've said that the velocity is equal to Ka. We can rearrange this, and don't worry about this is not something you're going to have to do. All right. But what this equation comes to is that the concentration of A in a first order reaction at any point in time, right, it's going to be equal to the starting concentration, which is A0, times E, natural base, to the minus kT power, minus the K there, which is the rate constant for a first order reaction, times time. So you can plot this in one of two ways. You can plot it, let's say, the concentration of A versus time, or the natural log of A to get rid of the E term versus time. Let's look over here. What do we know about radioactivity? A radioactive material. It has a half-life, right? So for P32, it's 2 weeks. For tritium, it's longer. Does that half-life change? When you are looking at a first order reaction, at some point in time, you start at the beginning with A0. At a certain amount of time, you've dropped from whatever A0 was at the outset, at the beginning, to 1/2 of that. And the amount of time that it took to go from your starting material to half of that is T1 half. At this point, if you're now going to say, starting with a half, I want a half of a half, which is a quarter, it's the same time, right? So you start with a certain amount of radioactivity of P32, 2 weeks later you have half. Another 2 weeks, you have a quarter. Another 2 weeks, you have an eighth, etc. So that curve, you should know, is an exponential decay. So an exponential decay is characteristic of a first order reaction or first order rate equation. So this tells you it is first order, and it will also give you the half-life. If you plot it this way, you get a straight line, and the slope of that is equal to minus k. So when you're thinking about the rate constant versus the half-life, do those seem like two entities that should be related to each other? Yes, all right. So the rate constant is related to T1 half, all right. Important point here is first order, you see this exponential decay, and you can plot it this way to get the rate constant. Okay, in most cases, when we talk about enzymatic reactions, we're not going to be dealing with first order reactions unless we're at certain points, which I'll show you. A zero order reaction is where the velocity is independent of A. And that would basically tell you that the rate constant was simply equal to the velocity. We're not really going to give examples of that. We're more interested in reactions of this nature. So let's say you have two reactants, A and B, and they're going to product. The velocity, if A and B have to come together, that reaction is going to be dependent on both the concentration of A and the concentration of B. So what did we say? The velocity now in this second order reaction is going to be equal to a rate constant times the concentration of A times the concentration of B. So the units of that are going to be different than the units for a first order reaction, right? Because ultimately, when we talk about the velocity is going to be, the units for velocity is what? Molarity over time. So if here you have two concentration terms, that's going to change the units of a second order rate constant. If we look at that reaction, now we can say, what is the reaction order with respect to A? It's dependent upon the concentration of A, so it's going to be first order there. It's going to be first order with respect to B, so then that reaction is second order overall. Okay? Here, let's say you have two molecules of A going to product. That would also be a second order reaction because you have two molecules having to come together, so if the concentration drops, it's going to be a squared function. All right? These are the types of reactions, though, that we're going to be most interested in. Okay, so now let's start to move to enzyme catalyzed reactions. In the cell, the enzyme is working on substrates, but the substrate concentrations can vary. So let's say we do an experiment. We have some substrate that's going to product, and now it's being catalyzed by an enzyme. So you should have some idea what that enzyme is doing structurally, but now we want to look at the kinetic manifestations of it. We do an experiment where we take our substrate and we do the reaction at, let's say, 3 different concentrations. One is a very low concentration. The second one, an intermediate to high concentration, and then this one even higher. So these are 3 different concentrations of substrate, and then we add the enzyme, and then we look at the appearance of product as a function of time. So early on, you'll see this quick rise, and then it will kind of plateau. That curve, is that curve telling us the points that are being plotted on the curve, are they rate or are they concentration of product? The points themselves that are being plotted. At a given point in time, you're measuring the concentration of product. So you're getting a curve which is showing you the appearance of product. But the important point here is early in the curve, that's when you're just coming out of the blocks, the rate of appearance of product is going to be higher, right? Because the velocity of that early has a lot of substrate to work off, right? As the substrate starts getting depleted, then the velocity of the reaction starts to drop, right? Because the velocity is dependent on the concentration of substrate. So in these curves, this dashed line is a tangent to this. That's projecting out, and that's telling you early in the reaction, when there's a lot of substrate there at the outset of the reaction, what is the slope of this line here? That tells you what we refer to as the initial velocity. So at that concentration of substrate, we give it the enzyme, and now we start looking at that early velocity. The velocity later is going to taper down because we're burning up the substrate. So we measure that velocity early time point. Now we do it again, but we have a higher concentration of substrate. So when we put the enzyme in, and in all of these cases, we're putting in a constant amount of enzyme. You put that enzyme in, and now you're getting a burst. Early on, everybody's coming out of the blocks, and now that initial velocity, or the slope of this part of the curve, is that higher or lower than that? It's higher. So because we've raised the substrate concentration, when the enzyme gets in there early on, it's got a lot more molecules that it can work on relative to this case, so the initial velocity or the burst is much higher. Now let's say we go to an even higher concentration of substrate. We can get to a point now where this curve and the velocity here is not really different than this one. Why? Because we have a constant amount of enzyme. So you'll get to a point where you've saturated the enzyme. So the enzyme can only grab, chew, spit out so much, and so in these points early, the enzyme is not saturated. So as you increase the concentration of substrate, your velocity is going to go up. You get to a point where it saturates out. So if it saturates out, at high concentration of substrate, let's say we have a certain high concentration. Then we do another reaction where it's 2 times or 3 times that concentration, and the velocity doesn't change, right? What order would that be with respect to substrate? At that point, 0. Right? It's no longer dependent on the concentration of substrate. It's dependent on the concentration of enzyme. So that is characteristic of an enzyme catalyzed reaction. And that is the order of the reaction is going to change as a function of the concentration of substrate, because you've got a given amount of enzyme there. It's working on the substrate. So at low concentrations of substrate, right? Let's back up. So here are 3 examples. I've done this experiment at concentration 1, concentration 2, concentration 3. I set up 3 tubes, 3 different concentrations. I give the same amount of enzyme to each one. I look and I measure the amount of product as a function of time. I'm taking the slope of the early part of the curve, which is my initial velocity or the burst out. Now I'm going to do this not for just 3 concentrations, but I'm going to do it for a number of concentrations of substrate. That's going to give me a curve. Does that curve look familiar? Okay, so this rectangular hyperbola is characteristic of an enzyme catalyzed reaction. When the concentration of substrate is low, bless you, what reaction order is it with respect to substrate? Is it dependent on the concentration of substrate? If you double the concentration of substrate here, you're going to double the velocity. So at low substrate concentrations, it's going to be first order with respect to substrate, but we also know if this is enzyme catalyzed, it's also going to be dependent on the concentration of what? The enzyme. So that's why it's second order overall. At all substrate concentrations, it's first order with respect to the concentration of enzyme. Now we get to a high substrate concentration. We're up here where we double or whatever the concentration of substrate, and we're not seeing that be reflected in a change in the velocity. At that point, at high substrate concentrations, we're zero order with respect to S, but we're still first order with respect to enzyme. So that's a first order overall reaction at that point. All right? All right, so this is what the curve looks like. Let's define some terms. This equation, Michaelis-Menten, this is an equation which describes that classic curve for an enzyme catalyzed reaction. So the velocity is equal to Vmax, which we are defining as the maximal velocity, times the concentration of substrate, divided by a term Km, plus the concentration of substrate. When you plot this out, we have seen there are 2 terms that we've already talked about that have kind of a similar feel to them when you think about them as Km. A pKa is what? It's a pH at which you have 50% dissociation. A P50 is what? Concentration of oxygen or whatever at which you have 50% saturation. So in both of those cases, you're talking about the concentration of this where you have 50% of that. Here is another term along those lines, which is Km, all right? Km, by definition, is the concentration of substrate at which you have half maximal velocity. So when you plot this out for an enzyme catalyzed reaction, you're going to reach some limit, and that limit is Vmax. That Vmax is at a given enzyme concentration, right? But that is where the reaction stops being dependent on the concentration of substrate, and you have this constant velocity up here, which is Vmax. So Km is defined as the substrate concentration at which you have half maximal velocity, all right? And we will see in other examples where we can actually plot data to determine Km, to determine Vmax, and that tells us things about the properties of the enzyme. All right, so again, let's just look at this equation. If the concentration of substrate is very, very low, right, then if this number relative to the Km is small, let's look at this term. If this number is relatively small to Km, then that denominator, for all intents and purposes, is the same as Km, right? You've got a ton plus a speck is pretty much equivalent to a ton. So the velocity when the substrate concentration is very low is Vmax times the concentration of substrate over Km. We don't remove that from this term because this is being added. So that is at this point. Let's say that the concentration of substrate is 1/2 Vmax. I'm sorry. If the concentration of substrate is equal to the Km at this point, if you put S and Km as being equal here, then what does that term simplify to? If these are equal to that, and that term are equal, then that's going to be 1/2, or the velocity is equal to Vmax over 2. Okay? So this equation accurately describes the velocity of an enzyme-catalyzed reaction when the substrate concentration is low relative to the half maximal point, when it's at that half maximal point, and then if the substrate concentration is much higher than the Km, right, then this term is a ton. This term is a speck, which essentially reduces down to a ton on the denominator, and on the numerator, it's Vmax times the ton. The tons reduce, and velocity is equal to Vmax. All right? So you need to know what Vmax is. You need to know what Km is, and you need to know that as the substrate concentration is changing, the reaction order is changing. So if the substrate concentration is well below the Km, the velocity of that reaction, and we're talking about an enzyme-catalyzed reaction, is going to be dependent on what? It's first order with respect to the enzyme concentration, first order with respect to substrate, so it's second order overall. The concentration of substrate is much higher than the Km, and you're way out on that curve. It's no longer dependent on the substrate concentration. You can continue to increase it and it has no effect on the velocity. The velocity is at Vmax, so that's first order now overall because the concentration of that Vmax, right, the concentration dependence is strictly being imparted by the concentration of enzyme. All right? Is that clear? Okay. So, some important features about enzymes, and we're going to get into much greater detail later. So, enzymes and other catalysts, as we've said, they function to accelerate these reactions by lowering that activation barrier, right, by lowering the delta G double dagger. The enzymes must bind their substrates prior to catalysis. So, when you think about it, I'll just give you, just to kind of think ahead, but you're not going to be responsible for this, what I'm about to say on the exam, is what does an enzyme have to do? It has to get its substrate, or substrates if it's bringing two together, and then chemically transform them. So when you think about how good is an enzyme, how efficient is an enzyme, there's going to be two things that are going to come into play. There's going to be one, which is how well does it bind its substrate or substrates? What's the binding affinity, right? And that's going to be determined by the kinds of interactions that we've been talking about, molecular recognition, charge, so forth and so on. Once it has the substrate, then what does it have to do? It needs to chemically transform it somehow. So if you have an enzyme that binds its substrate really, really well, that doesn't necessarily mean it's a very efficient enzyme. It could bind it really well. It has a very high affinity and it binds it well, but then once it gets it, the chemical action on it is slow, right? It doesn't transform the substrate that rapidly, and enzymes are meant to accelerate reactions. So if it can bind its substrate at really low concentrations, but then kind of sits and ponders, what the heck am I going to do with it, that's not a great enzyme. You've got another one that this enzyme is a chemical transformer. As soon as it grabs onto something, it's going to transform it. Its structure is perfectly designed that once it gets a hold of it, the chemistry is going to happen very quickly. But this enzyme doesn't bind substrate very well. It sacrificed itself and said, you know, I got a great car, and if I get a date, they're really going to love it, but I didn't get a haircut, I didn't take a shower, I didn't get any clothes, so I'm not, right? So the point is, when we get into thinking about enzymes and the strategies for them being efficient, they have to be able to do both. They have to be able to bind efficiently, and then they have to be able to do the chemical transformation. And we'll look at these enzymes, and structurally we'll see how is it that they can bind specific substrates. And in some cases, they'll bind related substrates, but not surprisingly, if the molecular recognition is conferring that binding, that the substrates are going to have fairly similar structures. And that's going to fit in nicely to a structure in the enzyme. And then the catalysis may differ. But this recognition, we will see, has a structural basis. And then once it has it, when we look at a few examples of chemical bonds being broken and reformed, we will see how it is that the structure of the active site that's doing the chemistry also fits with what it has to do. All right? And lastly, this enzyme's affinity for a substrate can be described by Km. All right? We will, I'll tell you now, Km is the concentration of substrate that you have half velocity. The Km term is in fact referring to the binding. We'll talk about another term called Kcat, which is the catalytic component, and we're not talking about that yet. All right. So these are some of the main features. Okay, so from lecture 1 to now is what you're responsible for on the exam. People have been asking about the exam. I'm not going to make a secret of it. I'm not trying to trick you, anything else. The point here is for you guys to learn this stuff. I will give you multiple choice. I will, you don't want to hear it? Or you can go if you want it. Amino acid structures you will be given. So I'll give you, if you need them, the amino acid structures with the name. I'll give you a pKa table, but I'm not going to tell you that amino acid is hydrophilic. That amino acid is hydrophobic. That much you should know. All right. It's a big class. You don't want to have wandering eyes. All right. So I'll be down here with graduate assistants, and I don't want to have to go through the exercise of, you know, catching people being dishonest. So don't do it. The exams are not all going to be the same. All right, I'll tell you up front. They are going to be multiple versions. And so if you're planning on, you know, question.
How many multiple choice questions?
I haven't put it together yet. Enough to fill your time.
Strictly multiple choice.
Yeah, we'll go strictly multiple choice on this exam. So the exam is on Monday, and there's a class in here before us, and there's a class in here after us. So get here on time. We'll talk again about this on Friday, but just think ahead, about getting here on time. Recitation tomorrow, 144 Farber. We will start at 9 and go at least to 11, maybe to 12 if people need it. Okay? See you.